to see all the colleagues. Some I know better than others. I've been working at the Technische Universität Eindhoven for a number of years now, and Eindhoven is completely English, which is probably my advantage because my Dutch is not as good as my English. So I do this presentation in English. And I'm a Hochlehrer there in mathematics, or also STEM education. And I'm working together with several people there in maths and science education. And Zeger-Jan, one of the postdocs who has been working with us for a long time. At the moment, he has a 6 months, I would call sabbatical from TUE, but he's working at Fontes. And then hopefully in September, we work together again on the project that we started this year. There's also Ulysses in the audience, Ulysses Hernandez, who came over from, originally from Mexico, and he worked with Louis Radford, and then also in Lyon with Luc Trusch, who is a good colleague of mine, and of Paul, of course. And there's also Aisha. Aisha joined us from Turkey. I don't know whether the PhD students are there, but anyway. So we would like to talk about towards innovative practices in higher education mathematics, and we would like to take the students' perspective there. The structure of the presentation is the following. First of all, a little introduction and the lens of resources. Second, student use of resources at university, and we talked about calculus and linear algebra. And from there, that study we use also for developing the notion of actual student study paths. And then we went into another course, into a kind of more innovative course, challenge-based education course, and we looked at student use of resources there and compared that to the traditional mathematics courses that we had studied before. And now recently we used a challenge-based education or innovative course in mathematics, the modeling course. It's a 1-week modeling week of 4th-year students. And then we would like to discuss with you, but please note that if you want to stop me in the middle, please do so. I can't see when you lift your hand or when you, so Rogier has to tell me, and then I stop. And or if Zeger-Jan wants to add something, Zeger-Jan, I also can't see you. So that's it. So the lens of digital curriculum resources, or the lens of resources in general. We, of course, started originally with the tetrahedron of didactical situation that is known in mathematics education, where you have the triangle of the student mathematics teacher, the didactical triangle, and what is added to it is the artifact. And for many of our studies, that was the basic sort of frame that we were talking, and you can see the different sides, the different faces of the tetrahedron, which of course give you a different situation and goal of study. So that was the artifact at that moment was mainly the textbook. And that was around 2000 or so. I did some studies together with Linda Haggerty, and many other people have done textbook studies, exercises or problems in textbooks, and so on. We did a comparative study, England, France, and Germany at the time. We would like, why I put the other one, you don't have to read all the stuff, is that we are going a little bit also further from the just classroom situation to look at the larger context. And of course, when we go from school to university, it's a very different context. And so I put the further developed tetrahedron here, which I don't want to discuss. I just want to tell you that we go larger than just the classroom situation later on. The lens of resources. What do we mean by resources? Basically, anything that helps students or teachers to develop their mathematical practice. And it started with Jill Adler, who talked about resourcing teachers' activity. And we then defined in the encyclopedia, in Lehrmann's encyclopedia, the notion of curriculum resources. That is Ghislaine Guidet and I. And what we used for our study, and actually one link is missing here, were the resources. We distinguished between curriculum resources, and in curriculum resources, they're clearly linked to the curriculum or to a curricular goal. So you have textbooks or other materials, you have digital materials, lecture notes, digital learning environments, and so on. But you have also social resources, human resources, whether it's peers, friends, tutor, lecturer, and so on. You have the cognitive resources of the mathematics, and in the mathematics there are methods and conventions that we call sometimes cognitive resources. And then, of course, there are general resources. We didn't find a better name for it, which the students identified. And in our case, they used at university, they use a lot of Khan Academy and so on. But so there should be and then there is a box underneath, is the link, the use, and there should, of course, be the link to the cognitive resources too. There was one little red arrow missing. So by use, we mean the selection, alignment, appropriation of those resources for particular learning activities, as indicated in our case by the students. So it could be orientation, revision, getting help, and so on. So that is that's where it started all from. It started from textbooks and went into resources. And of course, Luc Trusch and Ghislaine and I, we worked there a lot together. And now I can't change the slide anymore. Rogier, why can't I change the slide?
Maybe you have to make sure you're in PowerPoint again. Oh, there it goes.
Okay, yeah. So there are these different studies, textbook analysis, commonly used textbook, use of textbook by mathematics teachers. Then came the use of resources by teachers in school level. And then when I came to university, we talked, of course, to teachers, but we turned also to the student use of resources in higher education. And those are the examples of studies that we will present today. So, yeah, the first one is the student use of resources at university, and I hand over to Zeger-Jan Kock.
Thank you. Yeah, I'll talk about mainly the quantitative part of one of our studies on the use of resources by first-year students at university. Before I do that, I would like to make this notion of resources a little bit more concrete. And well, some of you may have seen this presentation before, but we will. We asked students to describe what resources they used to solve one homework task that they considered challenging. And one of our respondents came with the exercise that you see here. Yeah, and you can just click once more, please, or a few more times. Yeah. You see in red all the resources that the student mentioned while she was trying to solve this problem. And she refers to the lecture, the exercise itself came from a particular book. Can you click once more, please? She Googled, she looked up things in Wikipedia to solve this problem. And yes, next one, please. She also consulted her friends when she got stuck. And she consulted the calculus book. Yes, she asked a friend. Just once more, please. Yeah, and this is the final one. So she came up with a final solution. If I'm not mistaken, it's not entirely correct, but it doesn't matter. the message we can take from this is that she had one exercise and she used 6 different resources to solve that exercise. And some of the resources are curriculum resources prescribed by the university. But in particular, when she got stuck, she consulted other resources, social resources like friends through Telegram, for example, but also general resources on the web, Wikipedia, a file with word solutions that somebody put there. So students do things with these resources that that we may guess, but that we don't really know what they use. So we administered a survey among these first-year university students in 2 different situations. First, a calculus course, which was a very large course at 3 levels for all departments, students from all departments at the university, about 2,000 students, and a linear algebra course mainly for mathematics and physics students. And we asked them about the resources they used, the resources they considered most important for their studying of mathematics, and what they used particular resources for, in the sense that that Birgit just described. The data, that was the survey. In that study, we also conducted focus group interviews, but Birgit will talk about that later. I will focus mainly on the results of the survey, and even more in particular about whether across these different types of calculus and linear algebra, we could find similarities in the use of resources. Are there students who use resources in similar ways? So those were the, and can we somehow understand how they choose that? Now, first to say something about the survey, we had a total of 403 respondents there. We also asked about some background characteristics, like which major did they take, about their age, gender, how self-confident they were about mathematics, about their learning experiences at high school, and also about the resources they used at high school. And you see, first of all, what they said about the resources they had used at high school. And what you see in the diagram is horizontally how often they used it relatively, with the frequency increasing to the right. And vertically, you see how relatively important they consider these resources. And you see that in high school, it's the textbook that is by far the most important resource for them. And you see that the teacher, whether he explains problems or he explains content, was not so very important. Other important things were word solutions and also the graphic calculator, because they needed to use that during their exam. Now, and then we asked the same question for students. Oh no, Birgit, could you go back, please? Or whoever is controlling the...
Can I ask a brief question?
Yeah.
Where are the cognitive resources here?
Yeah, that's a good question, and they were not included in the survey. Yeah, so you won't find them. Yeah.
Yeah.
So you see calculus B. That is, let's say, the form of calculus that was followed by most students at the university, and you see that to some extent that picture is very similar. It's still the textbook that is important. That's the most important. The past exam papers, the word solutions, those are clear similarities. There are also some differences. You see that DLE, so the digital learning environment that was used at the university to provide homework exercises. There were also those were graded. They become more important. also you see that the calculator becomes far less important at the university level than at high school, because they were actually, I don't think they were even allowed to use a graphical calculator. So some of these things you can understand from how the work is organized at university. Also the teacher materials, and in this case that could be understood because the students said in the interviews that the textbook was really very abstract and complicated, and the teaching materials helped them to understand what was going on. So to some extent, you can understand the shifts in use of resources from high school to university. Now we ask ourselves, is this the whole picture? Is there maybe, when you look at these different levels of calculus and linear algebra, can we maybe distinguish students who think the same about the use of resources across these different courses? So we try to find clusters of students with the same ideas. And could you now please go to the next slide? So a traditional cluster analysis didn't work because of the way we had composed the survey. But with the help of a colleague from Italy, Domenico Brunetto, we were able to use social network analysis and then community analysis within social network analysis to find clusters. So we made like a social network of students based on their responses to the survey questions, and then we looked at students. We looked at clusters, at communities with social network analysis techniques within that social network. And then we found groups of students who had similar ideas about the use of resources. And that's on the next slide, the results from that analysis. The next, thank you. So we found 3 clusters. And 2 of those 3 were present in all the courses that we considered. And one of them was not cluster 2. You see that there was only 1 student in linear algebra, LA, that belonged to cluster 2. And probably that's a mistake, because cluster 2 was the cluster of students who considered the textbook the most important resource to study mathematics. The students in cluster 1, excuse me, that was the smallest cluster, they considered the teacher explanations the most important resource to study mathematics. And they also said that in high school they had found the teacher explanations the most important resource. The students in cluster 3 considered other resources the most important, apart from the textbook and the teacher explanations. For example, the teacher materials, the word solutions, the past examinations, and the digital learning environment. So these are the, let's say, the significant differences between those groups. Other differences, actually, we didn't really find with the other variables that were in the survey. So these were really more or less the only differences that we could distinguish. And that indicates that apart from the students in cluster 3, there are a lot of similarities with the use of resources at university in comparison to the resources they use in high school. Will you go to the next one, please?
Zeger-Jan, maybe while you're switching to the next slide, there is a short question in the chat. You probably can't
What are the teaching materials? Yeah, sorry. I see it, but I overlooked it. What the main teacher materials for Calculus B were the lecture slides. So the lecture notes, sorry. And basically, I think slides with annotations. They were. There were also some others, but these were the most important, and this was the one that was also mentioned by but specifically mentioned by students in the interviews.
Thank you.
Now, based on this cluster analysis, we made a comparison. And for example, within the same course, Calculus B, you can look at students within two different clusters. For example, cluster 1 and cluster 2, and you see that again the horizontally the frequency and vertically the relative importance. You see that the lecture explanation in the textbook that it is clearly different, and that from those students who consider the textbook the most important, who are in that cluster, they consider the lecture explanations actually very unimportant, although they're still rather frequently there. So they, to some extent, that means they are following the lectures, but they don't take much home from those lectures. They don't consider them very important for their learning. Likewise, and you see also that the students who consider the explanations very important, they indicate less frequent use of the textbook. So these are the type of differences you see between the clusters within the same course. Now, if you go to the next slide.
Can I ask another little question?
Yeah.
Because I personally, I don't really understand the cluster analysis, how the clusters were exactly made, but I sort of get the feeling, wouldn't you, it's probably wrong, but wouldn't you always get two clusters like this? If you're trying to make clusters, then you'll find whatever two groups you take, you will split them on some property, and then there will be this difference on that property. So
yeah, that's a very good question. Now, there, of course, you don't necessarily need to find clusters. It's also possible that it's just that there are no significant differences between the group. That's possible. In the second place, in this analysis, there are certain quality criteria that you can use to say, are these clusters really clusters? Do they distinguish? Can you really consider them as a group separated from another group? And then and these quality criteria, well, they were reasonably okay. So you could say that the clusters had some real existence. And the next thing you do is you try to understand. Let's say that the analysis comes back with, okay, we have three clusters, and these people belong to this cluster, these to that, and these to that. And then you try to figure out, okay, in what respect do these clusters differ from each other? And then you start to look at, okay, what comes up are these three, these qualitative descriptions that I gave. So one group finds this more important, and others certain things less important. And also, I think that the student who considered the lecture explanations very important, that they said similar things on the high school, in high school, that to me that's an indication that at least it's not purely coincidental that this cluster came up.
Thanks. It sounds like a very good method. It's very interesting. Thank you.
Yeah. And what you actually, okay, well, no, it goes too far to go into detail. I think that will be a different presentation. And what we could also do is to look at the same cluster, but then in different courses. And no, we go back, please. And that's what you see here. You see cluster 3. Those are the students who considered, let's say, other materials as the most important ones. And then you compared calculus B and linear algebra. And there you see, let's say, the correspondences, that the materials prepared by the lecturer, the past exam papers, etc. They mentioned that. But you see also some differences. For example, the students in linear algebra mentioned that the collaboration in class was a relatively important resource for them. And you don't see that back in the Calculus B group. And that has something to do with the organization of the course, because linear algebra was organized in such a way that students during tutor periods had to work together on solving particular problems. So you see, it's not just student preference that plays a role here. It's also the way that the course is organized and the resources that are offered to them. Could you now go to the next one, please? So that leads to the conclusion that this selection of resources by student is quite complex, and that secondary school experiences appear to play a role, for example, in cluster 1 and 2, but also the course setup and organization play a role, and the curriculum resources offered to the students play a role. And apart from that, the qualitative data seem to indicate that there are also sort of idiosyncratic ideas that students develop and habits, that's new habits that students develop when they work with resources, which we call the actual student study path. And Birgit will tell more about that in a minute. Yeah, and indeed, we also found this social network approach to find clusters very helpful when the traditional cluster analysis is not doesn't work. So this is what I wanted to tell about this story. Now Birgit will tell. This was in a very traditional setting, large calculus and linear algebra, and Birgit will tell now more towards the more innovative courses and the qualitative data.
Yes, thank you, Zeger-Jan. First of all, I would like to draw our attention to the actual student study path. So I stay within the traditional environment where we had some students which were also part of the quantitative study who did some interviews with us and actually some drawings. So the data collection strategies were then the individual focus group interviews, individual and focus group interviews, and we asked them to draw their resource system, which comes from another area or another notion in mathematics education, schematic representation of resource system that was developed by Luc Truche and Ghislaine Guédet in the documentation approach. We also examined, of course, document, we did observations, informal interviews with course leaders. So we wanted to know, how did students use their resources? We asked them that. And students had to draw. Now I'm explaining these drawings, but these drawings are only as valuable as they are in connection with the interviews. So we analyzed the interviews and we had the drawings. And this student said very clearly the first line of support is that she would go and see her friends. She would refer, of course, to the lecture, but mainly for orientation and overview, but not in depth to learn the mathematics. She sometimes didn't go to lecture. She used the video collator, and the tutor time, she fell asleep. And you can see that on the left-hand side. She also made a summary chapter and exercises. She looked at that, of course, the homework or the coursework that they had to do. And out of her own curiosity and personal interest, she looked at MathLab and other resources. So that was her. Then another student had used the book, the mobile and the book for his sort of at the center of it. We thought that was a kind of star-like representation. He referred a lot to people, group of friends and people, and also family. He was actually American, so he rang home occasionally to the tutor, and of course with relation to the test, but also a lot of YouTube and some lecture notes and so on. He also, in terms of communication with friends, he used video chat. And another one really took the lecture as the centerpiece. So the lecture was the centerpiece, not only for orientation, as we saw on the first drawing, but actually as the main part. And from there on, the student made notes and read about the topic, watched videos, did the homework, asked questions either directly to the teacher or on WhatsApp and so on. So quite different to some other students. Here, also, it's the person very individualistically worked, is me and the book, preparing for a calculus test, for example. Of course, reference is made to the lecture, but also to the exercises and the roommate. So there's Khan Academy as a reference when I don't understand, and so on. So you see that the student study paths were quite different. They were, and of course, amongst the students, we couldn't say which one was representative. So many looked for the weekly homework and tried to do all the homework. Tests and examinations became the focal point. However, one of the students, he was known to be an autistic student. He said, I did all the tests, all the homeworks and the weekly course, and I couldn't do anything in the exam. So it was not clear, unlike at school level, it was not clear that actually they had to develop their own sort of learning strategies and which resources to use and so on. And amongst them, as I already mentioned before, some of them really linked to the to the lecture and to the test directly, and there was the tutor time, but others directly to friends and peers. So it seemed that for procedural understanding, solving exercises and passing exams and so on, for the procedural understanding, they just tried to solve as many exercises as they could, or maybe passed exam papers and so on. There were weekly quizzes, but as we saw with one of the students doing all that, didn't pass you in the final test. For conceptual understanding, it seemed more that for them it was to understand the underlying thought or concept as they explained it. They used a lot of YouTube, also some of their friends and so on. So it was differently organized for different kinds of understanding. Then what we wanted to do is, of course, we wanted to see how would students organize their resources and which kind of resources would they select when they went to kind of innovative courses as compared to what we call traditional linear algebra and calculus courses. And then we used the innovation space. It's a special institute, you could nearly say, at TUE, bachelor and project. And in this innovation space, they run or support innovative courses. And amongst them is this IceBeb course, and that is this bachelor and project, which is based on challenge-based learning. So students have this huge challenge in front of them, and the challenge could be climate change, as large as that. And then the student group has to find their own challenge within those larger challenges. And there's a challenge owner, and there is an academic tutor from the different departments who also assesses the work at the bachelor and project at the end. And there's also from the innovation space a tutor who supports the students. So, but when we went to this innovation space and the more innovative courses like challenge-based education, or some of them were in other departments, they were project-based or inquiry-based, we were thinking, what do we actually mean by innovative practices? And when the literature talks about innovative or innovation, it's towards students increasingly develop agency and choice. Agency and choice are the words that come up most of the time. So in our case, it was in selecting and using the digital resources or other resources for their learning of and the study of mathematics. So this is seen as to enhance their feelings of empowerment, ownership, sense of purpose, for example, that they learn to direct their own learning. So self-directed learning is then, and so that at the end students can easily study according to what works best for them, and of course at their own pace. And students that are then allowed to direct their learning, in our case with particular resources that they choose or that is provided for them, and they can tailor their interests more. So it is hoped that students are more engaged in these kind of innovative practices for learning, and that they sort of lead to a kind of that development of their own learning or study paths. And there were 5 arguments given for involving student voice. Student voice is a big word as well. I don't want to go into that. We can do that later if you wish. So student agency was one of the big terms, and it refers to the level of autonomy and power that they experience in their learning environment. And it means really students play a critical role in their own development, what they learn, how they learn, and in their reflections. What I thought was important, or what we thought was important to note, is that agency is not just individual. So it's not just autonomous learning by themselves. It can also be exercised within social practices. And I gave here a quote: agency lies in the improvisations that people create in response to particular situations. And more recently, there are papers on not only self-directed learning, but co-directed learning and so on. And that is in another department at TUE. People have written about it. So just wanted to mention that. We thought what were if we look at the perspectives on innovative practice, we thought there were 6 notions that were important. So it was about student-centeredness, teacher scaffolding rather than teacher leading it, contextualized learning, relevance. Students see the relevance or for their learning, social interaction, whether that is between peers or whether that is between a teacher and the students, and continuous formative assessment. This is not hard and fast, and we can discuss it at a later stage. But we are in the process of using some of this, and in particular in challenge-based learning at TUE, we have another group of researchers has developed a kind of similar figure for challenge-based education, where it goes much more particularly into fields like multidisciplinarity and so on. But we think that challenge-based learning is not appropriate for all years at university, and maybe not even for all subject areas. And so we went a little bit further above it to think about innovative practice, and thought that this might be better for when you look at courses and when you fill in a cursor, how much it's student-centered and so on, that would help. But it is up for discussion, of course. So I just explained that, what we mean by innovative practices. Of course, the particular innovative practice is challenge-based education. Technology as the main driver, I skip here, but I wanted to talk to you a little bit more about the context and the research question for this particular study. So you've heard a lot about these earlier studies in calculus and linear algebra, and which resources students use, how to use them, how they use them beneficially. Now there was this emerging innovative practice at the university, and there are courses now using challenge-based learning or challenge-based education in different engineering fields, but also mathematics students. For example, this year in the ISPEP, the Innovation Space Bachelor End Project, we have, previously we didn't have many mathematics students. Now we have really somebody that comes from the mathematics department. So the research question was there, what kinds of resources were selected by students, and how did actual student study paths unfold in CBL projects as compared to traditional courses. So there's the bachelor and project, 3 years, academic and process supervisors, no prescribed resources. There were 6 students in this study, and there were 2 projects. One was the Parkinson project and one was the Garden of Resonance. So the Parkinson project was about students trying to find a measure or a help for Parkinson students before they come to this point of freezing this gorge. So that was their project. The Garden of Resonance was linked to acoustics, where acoustics was used in the artistic way of enhancing people's feelings and attitude in a kind of artistic way, and there was this musician working with them. So data collection strategies, we had those already before, they were the same, and we had these 24 students in the study here, and with the data collection strategy of drawing and so on. So the theoretical frames here we used were resources, as before, the actual student study path, and challenge-based learning. And the examples of, together with interviews, again, I have to emphasize together with interviews, those were the examples as one student described and drew the resources he used for the calculus course. So that is me, and then ik, and then asking questions, and the tutor, and the book, and online resources, and so on. Coming to the examples of the student of the schematic representations of resource systems in the IceBeb course, there was the tutor actually took on a crucial role, because they felt that before they were looking so wide, but to draw it together and to come back to the problem and to identify the problem, actually, that was one of their big issues, was the professor or the tutor helped them there a lot. So this is, we call these kind of schematic representations, we call them more cyclical and iterative, sort of going on rather than sort of star-like going out as we've seen before. In these courses, students have to deal with a lot of uncertainty. And this is really difficult for mathematicians in particular. Not many people want to do such kind of bachelor end project, and only the most assertive are trying it. And I said, so I was all by myself and looking it up on the internet and YouTube videos and the Maths Lab documents and so forth. The contrast, so like calculus and the physics ones, the contrast to lecture or tutor group courses, in those, the students mentioned that in those sort of traditional courses, I call them now, they actually teach you the tools to handle the problems. So in linear algebra, there was a reader and there were clear exercises. And if you do all those exercises, if you read the reader and if you try to understand it, then you will pass your test. What the format is now is they get a lot of information that you might use sometimes. So there's this huge amount of information, which is overwhelming for some. And not like, here you got it, and you can solve your problems with it. So I'm just trying to pass the test, but how can I pass the test? And so a lot of students were really lost with this kind of overwhelming number of resources, and and what to choose and how to choose and to assess whether they were useful or not. So that's why the tutor became so important. Yeah, they also talked about their previous experiences, and that's what you see in this quote here. I just passed the test at the time, and even if they taught me something about differential equations and so on, I just forgot it. So now I'm here at the IceBab course, and I have to reread it and to re-engage in that kind of. But of course, I've learned it in the first year. But nevertheless, I was just trying to pass the test. So it's a whole different kind of setup, and students are not quite prepared for it yet. So first, in summary, we could say the conclusions are first year calculus, linear algebra. They're good for gaining confidence with mathematical concepts. Curriculum resources are mainly used, digital and traditional, and various actual student study paths were identifiable to master the prescribed content, and in particular towards exams. In the CBL course, in the innovative course, students had to deal with uncertainty in task and process, mathematical modeling and signal processing. Using tools were given to them, and some of them they had to re-engage. Cognitive mathematics resources were really a precondition. Well, you have learned that before, and that should be with you throughout your studies. Digital resources to understand the problem or to learn to use the tools. Sometimes they were referring to not the university courses, but actually practical experiences they had with some of the digital tools elsewhere. Like one student I remember was talking about PSV, where he was working, and there he used a lot of digital tools and how to use these tools, and that's what he used for his IceBab. There was a supervisor feedback they valued. The challenges are that supervisor competences, and in mathematics in particular, go beyond specialist knowledge. The mathematicians in the mathematics department say that they feel a bit out of their depth to go that far, and that they're not specialists in all kinds of mathematics that might be used for this project. So the challenge is not only to help and guide the students, but also to bring the lecture and tutor group courses that are given maybe at the beginning of their bachelor education closer to the kind of CBL approach or innovative approach that the students might face at a later stage. And then last but not least, and I'll be quick, is challenge-based education in mathematics. Well, it's not completely challenge-based, but it's definitely problem-based. And we thought it was the best in terms of openness and also student engagement that we have seen up to now. And that was a modeling course that is always given at TUE for 1 week in November, typically. And it's called the Modeling Week. And it's a 1 week intensive course for first year applied master students. So they're in their 4th year altogether. The problems are set by external problem owners, and there are also supervisors from the department. So the students are divided into groups, and they can sign up for particular challenges or problems. And sometimes they're also put into groups because that's what they have as background, you know, for attacking these problems. The research question for us was, what are student learning experiences? And that is our big theme at the moment, student learning experiences in innovative courses, and here such as the Modeling Week. We're looking also at other courses, but this data is from the Modeling Week. So that was only in November, so we're not very far here, but we did observations there, 1 week observations. They had general meetings, they had group meetings, the student groups, there were groups of students. And Also, they had meetings with the maths tutor and with the stakeholders, with the problem owner, you could say. I should use the same term. So we had interviews with students in groups, to a lesser extent with individual students, with maths tutors, with the problem owners, and with course directors. And the students drew again their systematic representation of resource systems to support the interviews, as we had done before, on selection and use of resources, but we actually asked them slightly differently how they actually worked throughout that week, and how their understandings developed on this particular problem, and of course which resources they used. For the first time, we used exit cards, and exit cards were at the end of each working day. They had to answer 4 questions on an exit card. You will see that later on, where we asked them how they understood they had moved on in their with their project, what went on, how they felt about it. So there were 4 questions. Of course, we have documents that we analyze, like the Studievisor, and we took photos also from board representation. And of course, later when they hand in the reports, we'll also see the reports. Very small glimpses into their representations and interviews. Now, this student made a very discreet drawing, which really reminded us of what we had seen previously. So the resources used in the project, she or he was very clear about the different kind of resources used, whereas others drew more of sort of their progression. And so with these students, you really see getting to know the problem, implementing the basic problem, extending upon the basic problem results, and then sort of iteratively improving on that, and also with some notions about what kind of resources they use. Slider problem owner, chemical downloads, and slides, past courses, scientific competition, and so on. So you can see that. In another one, you can see a very vivid picture of where people came in and what they did on day 1 and on day 2, 3, 4, 5 was day 5 was the final presentation that they had to present. So out of the 6 students or so, 1 or 2 had to present, and only on day 1 they had to be confronted. So it was really a steep learning curve for those students. I give maybe 1 or 2 more, again divided into phases of Monday, Tuesday, and Wednesday is like one phase, then Thursday and Friday. And there were different kind of resources mentioned, but it talked a lot about brainstorming and start the work and change of plans and so on. And in the case of Becky, I wanted to give you the representation of her resource system, but I thought it was quite interesting that she divided it really into phases rather than the days that we had seen before. And there was the problem description between each step, time to ask questions about the problem and what were the resources. Problem owner was the resource. The problem owner was a huge resource for the students. Also the academic tutor, the mathematics tutor. And in one case, actually, the mathematics tutor and the problem owner was like one family. And that also one was still at university and the other one had gone into industry and given the problem. This is from industry. And of course, they work very closely because they came from the same institution and they were also discussing probably things. So that was a huge alignment of ideas and support and so on. Now, these are the exit cards that we had, and that was the first time we used of the same students. That was Becky. And yeah, you can see a little bit. The exit cards give you some idea of how they move, but we felt that the exit cards, together with the schematic representations and sort of drawing of how they moved on and how they developed with the project was very useful. I don't want to go into details here. So where we are now is that we actually look at what previously has been called critical incidents, because the students describe these during this week, these critical incidents, and we named them critical didactical moments determined by the students. The students tell us when these moments were. We're basing it on these qualitative accounts of students and analysis of critical moments in their learning process. The emphasis is on the depth of understanding of this particular phenomenon, the dynamics of the negotiations between students in the group, maybe between teacher or a tutor or challenge owner or a problem owner and students regarding the co-construction of meanings. And that happened actually a lot, and sometimes more with the challenge, the problem owner, I should say, and sometimes more with the tutor, in order to grasp, we want to grasp their learning experiences in the modeling course, and we're looking at methodological tools, of course, there. So during the modeling processes, we're looking at these critical didactical moments or incidents that affect change in the activity of the students, and of course, which resources they're using there and whether the resources are changing. So are there specific resources that are particularly useful or not? I think we leave it there, and we can't draw any more from the modeling week. You heard all the conclusions from the other studies, which have been developed, of course, and analyzed properly. And we would like to go on to a discussion, if we may. Thank you.
Thank you very much, Birgit. And I think Anna will lead the discussion, right?
Okay. Shall I, that I see a little bit more the participants, shall I take this off? Shall I stop sharing, or do we need the...
Let's see, maybe you can stop sharing for the moment, and then later if we needed to put it on again.
Okay, good.
Yes, thank you very much for the presentation. It looks like you are still sharing the screen.
Am I?
Okay, no, now it's gone. Yes. Please feel free to raise your hands and ask questions, and also maybe some comments if there are some. I think the best way is to raise the hand. You can also put them in a chat. And maybe while everyone is thinking, I will ask the question that I have already put in the chat, and Zeger-Jan answered me a bit, but I'm still curious, how do you see this innovation approach and its specific application within different subject domain fields? Can you say, like, generally it is student-oriented, empowering, agency triggering, but within mathematics there is something specifically important?
Can I try to say something about that? You see this movement towards things like challenge-based education in many technical universities, and I think there are several things driving it. That is, in the first place, maybe nowadays more than in the past, it is easy to make to construct working prototypes with relatively cheap components like programmable electronics and things like that. So students can, at a relatively early stage in the curriculum, they can be brought in contact with sort of authentic engineering tasks. And then there is the idea of that it is motivating for students if that has if there's a clear demand for it. So there is, for example, if it is linked to a particular problem in society, and if they learn to work together, which is also something they will need to do in their professional practice. So those are things driving this development. And then you get to the question, okay, but if we let students work on these projects, and very often they have to define, they're given a grand challenge, and they have to define their own particular question from that grand challenge. How do we make sure that they develop the required disciplinary depth? Mm-hmm. So that's one thing, and I mean that's still something under discussion at the university, and at what level can we do it, and at what level can we not do it? And when you, and then it depends a little bit on the particular domain, whether that is an important question or not. It depends on the disciplinary depth that is present in the domain. For example, industrial design, which is very much a process-oriented study, that it may be less of an issue than in physics or in mathematics. Mm-hmm. And then there is in mathematics there is also there are other let's say the mathematics department, I think. How should I say? Well, you want to avoid that mathematics students are used as a sort of people who do the calculations. They have to do proper mathematics in the sense of developing mathematical models and evaluating them, and maybe proving the existence of particular solutions and things like that. And that's often not so easy to find for challenge owners from companies. That's why we were happy with this modeling week, because there the people from the companies, they work together with the mathematical department to formulate challenges that are suitable for that student group. So they're not, and what you also see is that some of the challenges are tweaked a little bit, or maybe slightly simplified to make them fit into the knowledge range of the students. And with the bachelor end project, that's often not the case. They're just the tweaking is much smaller. So those are the type of questions that you need to consider when you use this approach.
And maybe to add, there was of course a big question, or is still a big question. Can we teach mathematics through a challenge-based approach? Can we teach the mathematics? I mean, the whole curriculum, basically. Can we teach the whole curriculum? And then the question is mathematical knowledge or mathematical theory the same genre as in, for example, in physics or in chemistry, or then we go to design or electrical engineering and all these things. And so that was a big question for a long time. And we asked, of course, the students also in the modeling week. I mean, they were in the fourth year, and the students said, in terms of mathematics, we didn't learn anything more. It was very clear. The students, they didn't learn anything. And then we thought, yeah, well, we thought that actually they were very engaged and they were learning. But of course, the understanding of knowledge and theory is very different in different departments. You know, mathematics, you have this body of knowledge. Well, the physicists, you know, there's a lot of empirical stuff and so on. So there was this question, and then we looked at venue again, and I'm sure that Paul will join us there. In some ways, the French theory, who explains that knowledge is basically, it's a conceptual field. It's not the concept individually there, but it's a conceptual field, and that with the kind of different situations, of course, add to this conceptual field. And so so they have added to their knowledge, but in a different way than we perceive at the moment, sort of knowledge maybe, huh? So, but in terms of venue, I would definitely say that they have gained knowledge in the modeling course. So we were mulling this over, and I don't know whether Ulysses, do you want to say something to that?
Yeah, actually, yeah, take into account, for example, this from Brecknio is actually there, for example, that there is the operational form of knowledge that also it could be related with the environment and how they interact with different tools, with different resources. And perhaps the students, they didn't think that they were learning something. But in a way, there is a specific form of knowledge that is the operation and how they interact in their environment. And of course, there is the predicative form of knowledge that perhaps is the form of knowledge that the students were more thinking about. And in this case, they thought that they didn't learn anything, but they didn't consider the other. I mean the interaction between these two kind form of knowledge that actually we would like to continue to look deep in, because as Professor said, is something that to take into account the different perspective of the knowledge. The knowledge is not only like the for example the predicative, that how to proceed in certain kind of things, also how we interact in the environment and with the different tools.
Thank you very much. Very interesting additional nuances, and I think a lot of consonance with also secondary school attempts to transform the education. But I would like to give the question opportunity for Argyris. Sorry.
Yeah, thank you very much. Great presentation, great work. I would like to ask for you, maybe you could elaborate a little bit more on how did you analyze the drawings of the students? I mean, did you set inductively some criteria or?
Well, this is a question that comes regularly when we show the drawings, because the drawings catch your attention, you know, but how to analyze it is not so clear. And we have not found a very robust way of analyzing. The only thing we say always is that we use the drawings with the interviews, so we understand the interviews much better, because we at the same time see the drawing, and the students, while they're drawing, they also talk and so on. So that is at the moment. But now that we have the exit cards as well, and the drawings and the interviews and so on, I think we should go a little bit into the potential of using these kind of methodologies also visually more, we started compiling literature on drawings. You know, you have a lot of literature on children's drawings, primary school and so on in mathematics, but it's similar, you know, in secondary school and university. This would apply as well. I mean, it's for us, it's a reflective tool. It's a tool for reflection, really, you know, because whilst they are talking or when they're talking, when they're explaining, they're reflecting. So we don't only have their words, but we also know that they have reflected on some of this before you start drawing, or so you think about what you're drawing. And some of them say, oh, I have to start again because this is not exactly what I want to say, or it's not big enough, or something like that. And then so it helped us to understand the interviews, but I think it's also a tool, a real tool that is there on the table when you talk to the students, that helps them to reflect.
So what we do is we often have these group interviews, and we ask at the start of the interview, we ask the question, and we give the students about 10 minutes to draw. And then when you look at the drawing per se, there's a risk of over-interpreting what is there. You might look at the arrows, and so we ask after the drawing, after they made a drawing, we're asking to explain what they've drawn and why, and we can maybe ask additional questions. So in that way, we can use information from the drawing itself and from what the student explained about it. And this makes the whole picture a little bit richer. But the risk is just relying on the drawing by itself, because then you run the risk of overinterpretation.
Yeah. In case there's time, I can have a second question, or maybe someone else wants to ask.
Not yet. You can use this.
In STEM education, it's quite common to begin with a challenge and what you call challenge-based learning. But to what extent it's similar with what is really cultivated as a problem-based learning? So, of course, problem is not the same as challenges, but I see that many STEM teaching begins with challenge.
Yeah, it is. If you look at the literature, it's all under the umbrella of inquiry-based education, so to speak. So the differences are a little bit subtle, but in problem-based education, the problem is often set in such a way that it evokes a particular line of thoughts of a particular line of action with students. So the problem is often set by the teacher or by someone external, by someone who has a certain learning path in mind. Well, the challenge is more open in that respect. Ideally, the challenge comes from someone outside of the university who has a real problem, and then those problems are often too big to be solved at once by such a group of students. So within that grand challenge, the students have to, from that grand challenge, the students have to derive that small part that they will actually work on. So that means it's much less predictable what the topic of their work is going to be, because it is, of course, the coaches have some influence on it and they can steer them to some extent, but a lot of autonomy in that respect is with the students.
So in other words, it's about the openness of the problem. And so and that gives students problems. Sometimes it takes them 6 months before they can identify, before the group can identify their particular problem within the grand challenge.
Thank you. I think that's an important clarification. And Paul has a question. Okay, good.
Yeah, thanks for your presentations, and it's a fascinating body of work with different sub-projects, but with one common aim of better understanding higher education, I guess. And I appreciated nice methods with the drawings and the interviews and the exit cards. It's really nice. What was not completely clear to me, also maybe because of time constraints, was this idea of critical didactical moments. I think it's very interesting, but could you just give an example or clarify it a bit?
Yeah. I mean, this is fresh from the press, or what do they say?
Yeah, that's why it's interesting to discuss.
We were thinking that Ulysses and Zeger-Jan and Aisha and I were looking at their drawings, for example, and there was to one extent there was some. They use these phases, so we suddenly were confronted with these phases, and they were sometimes from day to day and sometimes from, covered 2 days, or they describe them otherwise. Well, when you have phases, when do you change phase and why do you change phase? And that's where these critical moments is. Of course, Luc Trusch, there was also one paper where we talked about where the teachers went, when they have this trajectory, you might remember that paper, Paul, when they have this trajectory and they have these different sort of phases and they're critical moments or so. So that was sort of the input for that, and that's what we are looking at. It might not lead anywhere, I don't know, but I think when you have phases, there must be critical moments that you define these phases, and that you don't just just give the resources or something like that. And we thought that we have to dig a little bit deeper into that, what might be the moment, because it's all the students who have defined this. We haven't defined these moments. It's the students who decide. So we want to use it. We want to understand students' learning experiences in higher education mathematics, but in particular in these innovative environments. So I think that at least intuitively there are phases already where they, when we had the iceberg already, where they were going round and round in iterative cycles and so on, and now they're even drawing it, you know, when they go through this modeling course, and what can it say about the resources that they need? Do they use different resources for those or not? And how do they come from one to the next stage? Maybe it has to do with their cognitive development, even in the modeling course, or is it only with that they come closer to the problem solution or something like that? It's.
Can I add something to that, Birgit? We also did observations. We didn't really talk about that, but during that week, that modeling week, we visited the groups every day, maybe for an hour or so. In particular, when they had meetings with either their coaches or with the challenge owners, and you could see in some situations that they had a discussion with the with, for example, their coach, and from that moment onwards, they all started to use a particular terminology that was introduced by that coach, and that you could consider a critical moment. Or they thought they had solved the problem, but the coach mentioned some different approaches where they could solve the problem in a better way, and they started following that path. So the interactions with the coaches and the problem owners are really moments where they shifted their direction during that, and there may be other situations as well where their interaction with particular resources did something similar and shifted their direction during their solution and developed their, their solution path in their work.
And of course, it was so compressed. It was like a pressure cooker this week, you know. It was so compressed that they had to move on somehow towards the solution. And the problem owners, as they were, some were working more and some were working less with them, but you could see the influence of it that they brought, and sort of to move them on towards the solution. I think we were lucky in the sense that it was 1 week, you know, because I don't know how the students would have behaved in 2 or 3 weeks, because they said they learned a lot, but they would have liked to have more time. But yeah, it depends, you know, whether you need more time or whether in the week it's all there, and you know, day and night you're moving on to this with this.
But I completely understand that this is work in progress, and I think. But what I like in this idea of critical didactical moments is that it sounds so attractive, in the sense that if you teach yourself or if you observe a lesson, you have this feeling that at some point it's really happening. Like, and so it's interesting to know also in the case of your modeling course. What is it that causes this? So I was fascinated by this term. I don't know if there's any literature about it. I would expect so, but I don't know myself.
I remember only this. I remember this psychology person, but I remember also in England there was a person who had critical moments, but it was not in mathematics education. But in the meantime, you know, we haven't searched the literature far and wide for it, so that will happen. We just sort of latched onto it. I mean, intuitively, like you say, it might also be that with some students, if you think of venue again, if you consolidate the knowledge with so many different situations, then you move on. You know, then it's saturated or so. Then the richness, you know, can hardly be increased or so. And then there's the next move. But yeah, to to be followed, Paul.
Thank you. There is a Peter Pop sending in chat some relevant literature, so that's nice, maybe helpful for everyone here. Yeah.
Could I say just one short phrase, Anna, if you allow me? So thinking about Alison Clark Wilson's work on using digital technology, and she has this notion of hiccups, where hiccups are, well, initially a bit annoying things that happen, but that then cause this kind of, well, critical event to happen maybe. So there was a kind of maybe, even if the entrance was a bit negative, namely technology doing something unexpectedly or something that you didn't want to do, but that caused kind of critical thinking. Thanks.
Yes, but I think Alison, does she mean more, I mean, with technology and so on, she's on the technology there, no? Or is she, I don't know.
So that's quite, it's not the same, it's quite specific, but still there might be. It was an association I had in mind.
Yeah.
Okay, well, there are not more hands. I still have a list of questions, so if you don't mind, I will ask one more. So I was really triggered by the situation that mathematics teacher need a knowledge beyond specialist. And my question is the following: what kind of competences you actually envision in being able to conduct this study? Because it could be that it's not so much about just knowing all mathematics perfectly. That's probably not possible, but rather being able to investigate together with a student, to guide students for some specific resources or something like this, more of a meta level competences.
Yeah. I mean, it goes. I think in some ways it goes also into the didactics of mathematics, of course. Not the pure mathematics, but the didactics of mathematics, and the other part is, of course, in the use of resources, for example, also, like you said, that they have particular programs or something like that, but yeah, I think the mathematicians are used to having this security of having either you know it or you don't know it or something like that. And I think that sort of works against this kind of involving themselves in challenge-based or in some of these innovative courses. But that's why we were so happy to be with the modeling course there, with the modeling week, because there were more closer problems, but nevertheless it was the mathematics department has huge connections to industry at Eindhoven. I mean, it's the best of all the departments in terms of connection with industry, and the students are going out into these jobs, and so there is enough room and enough playing field also to develop this. And in any case, if challenge-based education says we need this open challenge, and the mathematicians say, well, it doesn't work for us, we use problem-based education or something similar, well, then it just means on the cursor, if you have a continuity, then the openness is reduced, but so be it. Every department has its constraints and affordances, I would say.
Yeah. Sure. It's also interesting that maybe mathematicians need to adjust a bit their self-estimation and vision of themselves as professionals. Peter, very nice. Maybe this is the last question we will take for today. Please go ahead.
Okay, thank you for your nice presentation. I like it very much. I want to go back to the first part where you defined different categories of students who prefer their resources. Did you try to find relations between successfulness of students and their choices?
Yeah, that's a good question. That was our intention, but we did not have direct access to the results for the course, so we couldn't do that. We did try to. We asked them for their results at high school, at a high school exam, and we tried to connect that, but we couldn't find any relation there. So that no significant relations were found. So that was one of the things, that apparently the clustering could not be connected to to previous success again.
Okay.
And also not to their mathematical confidence. So how well they thought they were themselves in doing mathematics, because that's something we did ask, but there was no connection, no significant connection.
Okay, thank you.
Very interesting. So it's like really individual passes.
That's one of the things that we say. It's a complicated process, and there's some idiosyncratic in a way. It depends on the person to some extent.
Yeah, very much in line with complex dynamics systems view on education as a complex process.
Now I must say there is still some development in this cluster analysis approach, and so it may be in the future possible to even more clearly distinguish those. The method we used is known for not being able to distinguish small groups, and there are other methods that could do that maybe better in future.
Okay, thank you very much, and good luck with the future things as well. That was very fascinating presentation with a lot of insight and things to think about. Also, it feels like your methodology of drawing and interviews will be further in the field. That's how it feels. So thank you very much once again, and I think that Rohir will shortly announce the next presentation.
Before you go, let me briefly advertise next month's talk, which is by Desiree Achterberg, previously known as Desiree van de Boogaard, and she'll talk about the use of history of mathematics in mathematics education. You're very welcome to attend again. It's, I think, in precisely 4 weeks. So we'll send you, of course, an abstract and a title and a link again soon. So thanks again for being here. There's the traditional after party, which is still not super popular, but maybe today is the day. So if you want to talk a bit more to the speakers, please stay, and otherwise you're free to go.
Okay.
Thanks.
I am stopping the
Thanks
recording.
again, Birgit and Zeger-Jan. And the video will be